give everyone just one more minute. Seeing some people who are specifically interested in ion traps and quantum information hardware. Cool stuff. All right. Why don't we go ahead and get started? Okay, so hello for everyone just tuning in. My name is Olivia Lanes. I am not your usual host, Lako Minev. He is tied up due to IEEE Quantum Week, but I'm very excited to be filling in for him and to formally introduce today's speaker, Professor Rajamani Vijayaraghavan. So we're thrilled to roll out the latest episode of the Quantum Seminar series, which is dedicated to the research and the academic quantum communities. This seminar is going to take place every Friday at noon Eastern Time right now, and is hosted on the KissKit YouTube channel. I am your host for today. Like I said, my name is Olivia Lanes from IBM Quantum, and I'm going to introduce today's speaker. So Vijay completed his bachelor's degree in physics from St. Stephen's College, Delhi University. He spent more than 2 years after that at the University of Cambridge before starting a Ph.D. at Yale University in 2001. Excuse me. After his postdoctoral work at the University of California, Berkeley, Vijay returned to India and joined the Tata Institute for the Theoretical Research to start a new laboratory. He currently heads the Quantum Measurement and Control Laboratory, where the main goal is to develop techniques to stabilize quantum states against decoherence. And he's going to be talking to us today about quantum information processing with multimodal superconducting circuits. So welcome, Vijay. Thank you for being here with us today.
Thank you so much, Olivia. It's a pleasure to be here, and thanks to the IBM team for inviting me to this KissKit series. These past 6 months have really been quite crazy for everyone, so I'm glad all of you are able to join in. But as I was just saying to Olivia earlier, that this has also given us this unique opportunity to having talks like this. The technology was there, we were just not using it. So I think there is at least some kind of a silver lining under here. So good to be here in front of such an international audience. As Olivia said, I'm a professor, an associate professor at the Tata Institute of Fundamental Research in Mumbai, where I've been here for about 7 years now, a little over 7 years. And of course, like most professors, all the work is done by the PhD students and postdocs, some of whom are listed here. There's a fairly large list of alumni now have no more space on the slide to be put in. But I'm thankful to all of them for putting in the work to get the results we have. I would also like to thank the funding agencies for providing the support. So I'll tell you about one of sort of the main focus of our lab, which has been the last few years, I think about 3 to 4 years now, on using multimodal superconducting circuits. And here's a brief outline. I'm assuming this is a fairly expert audience, so I'm not going to spend too much time on introducing the very basics of the superconducting qubit field itself. But I will very briefly introduce and motivate why we are doing this. And then I'll spend bulk of my talk about this new device, which we have named Trimon, which is a multi-mode superconducting circuit. And I will present to you theory and experimental results, which sort of tells you that this is really a fully connected and a programmable 3-qubit processor. And then towards the end of the talk, I will tell you on some of the ideas and some preliminary results where we are trying to use this as a building block for building larger processors. So let's get started. The transmon, it's everybody's favorite qubit, definitely the most popular qubit in superconducting qubits. And it's nothing but a nonlinear oscillator. I always find it fascinating that how the transmon came so much later into the development of superconducting circuits, but it's one of the easiest to understand. It's an oscillator, and we're using the 2 lowest oscillation states as the qubit. And the little bit of nonlinearity which comes from the Josephson junction allows us to separate it from its behavior as a harmonic oscillator, and that's where you can isolate the 2 lowest levels. The higher levels are always present. One has to be aware of them. Sometimes they are a problem, sometimes they're actually useful for doing certain things. but mostly your dynamics can still be defined as an effective two-level system, hence a qubit. Um, the nonlinearity is of a form which is very similar to a pendulum when you think of a pendulum for arbitrary angles of displacement and not just small angles. It's exactly the same form of nonlinearity which give rise to this cosine potential and the sinusoidal restoring force in a pendulum. And again, I'm sure many of you have seen this. In our lab, we have mostly been working with the 3D transmon, which is quite big in size. So here's a picture of a device made in our lab. It's a tunable frequency transmon shown here with two big pads and a squid loop in the middle. And we all know that typical parameters of these devices give you inductances and capacitance in a range so that you're working in the microwave frequency for the oscillation of omega 01, which is around 5 gigahertz. Have to put everything in a dilution fridge so that you, of course, first get superconductivity, and then you also suppress thermal fluctuations so that you can really work with the two lowest levels in this transmon potential well. Okay, and for doing anything more interesting in quantum computing or building quantum processors, we have to couple qubits together. And a very simple way of coupling these kind of qubits, which are just oscillators, is just put a capacitor between them, and now you have a coupled oscillator kind of system. And this has been the basis for most of the kind of qubit architectures which has been around. This capacitor, of course, now here is sort of representative. So you can use that typically when we have nearest neighbor coupling. So two devices sitting next to each other coupled via a capacitor. If you want to place them further apart, you introduce a resonator, which is often called the bus cavity or the bus resonator, for long distance coupling. So then that way you can spatially space these things apart if you would like, and then you have more flexibility on how you connect them, and that gives a nice way of making larger circuits. Even when you do that, there are a couple of different ways you can actually do the two-qubit architecture. Typically, this kind of coupling, we call it transverse coupling or dipolar coupling or exchange coupling. And there are the fact that the coupler is always present here. So these are not couplers which can be turned off. So this is one of the most commonly used architectures. The ability to effectively turn off interaction comes from the fact that we keep the resonant frequencies of these two qubits separate. They are detuned, and then they can sort of work effectively as independent qubits, though as we all know that it's not really such a perfectly isolated qubits, even when they're detuned. And that can actually give rise to a lot of errors. And in fact, some of the work from the IBM group has been to figure out ways to work around that. And so when you do want to create an interaction, a real interaction so that you can do a two-qubit gate, then you can either use tunable qubits and tune the frequencies so that you can bring these oscillators into resonance and do some kind of an exchange-based gate, or you apply specially chosen RF tones on one of the qubits, and that sort of creates an effective interaction only when the microwaves are on. So this gives you two different ways, typical ways, and there are variations of how you can apply these RF tones to initiate the gate. And again, this is not the whole picture. You have tunable couplers where you can actually turn off the coupling by introducing more complicated circuits instead of the capacitor or the resonator shown here. And these are broadly sort of the two common approaches used for coupling qubits, and it's been quite successful. Here are some pictures from a while back from the Google design and the IBM design, if you would like. This is an old 9-qubit chip from, in fact, UCSB, which was later on used at Google as well, where the qubits are placed in a linear array, and they are nearest neighbor coupled because of capacitances. Whereas the IBM Q design, here's one for a 16-qubit, uses bus resonators to lay the qubits out in a 2D grid, and then you can connect them in different ways. And here's one particular choice they have made for these qubits. And the thing to note here is that in the first choice, the it's a linear array, so the qubits are only coupled to the nearest neighbors in a linear fashion. And here you have a little bit more connectivity. Each qubit is coupled to at least a few more qubits, depending on the choice of the resonators they have made here. And of course, there are variations of this are possible. But typically, the connectivity is limited. It doesn't go quite far as the qubits are further and further apart, which of course in a multi-qubit processor, you need to lay out the qubits in some form. And I want to compare this with what's happening with trapped ions, where even though the ions are actually trapped in a linear array, it is actually possible to create an interaction between every qubit, every pair of qubit in that system. And recently there was some result. In fact, this is a little old now. There was some major news a couple of weeks back about a processor from, I think, Honeywell, where they have many more qubits with a lot more connectivity. But IonQ had talked about some 11-qubit system, which is fully connected, which means you can do gates between any pair of qubits in the system. And this is, actually an important feature of any processor, because generally when we think about algorithms, we don't often think about that you might have restrictions on doing gates between certain pairs of qubits, or that to do an effective gate between qubit 1 and qubit n, you might have to do many other operations. And that can actually have an impact on how an algorithm is run. And particularly when the systems are prone to errors due to decoherence, having additional steps for running the algorithm can be detrimental in principle, right? So if you have higher connectivity, you can run the same algorithm in less number of steps. Okay, that's sort of a simplistic picture. And having the possibility of doing gates which are higher dimensional, so in the sense that the kind of picture I presented in the previous slide, that we are talking about only 2-qubit gates, though for universal quantum computation, that's all you need. You need 2-qubit gates and a bunch of single-qubit gates. And you can effectively represent any algorithm using these elementary operations. But having the ability to do maybe higher dimensional gates can give you some advantages by, again, cutting down on maybe overall execution time and doing these things more efficiently. So that was sort of broadly the kind of goal we were working towards, and it's still an important focus of research in our lab. So with that, I want to introduce this this device, which we called a Trimon, and it's basically a 3-qubit circuit. So it's not 3 different qubits, it's a single qubit which effectively behaves like a 3-qubit circuit. And you can see that it's just slightly more complicated than a transmon. Okay, so a transmon typically has a single junction and a capacitor. And now what we have are 4 junctions, placed around in a square like this. And then each of the vertex of this 4-junction square is connected to the, every other vertex with capacitor. Okay, so the CCs are the sort of the capacitances shunting the junction directly, and then you have the CA and CB, which are the diagonal things. And from the point of view of fabricating this, especially in the 3D geometry, it doesn't look much more complicated than a Trimon. Trimon just had 2 big pads and a squid in the middle. Now we have a sort of a system with 4 junctions and 4 pads. And essentially, all these capacitances are obtained by just understanding how these different pads interact with each other. And I will come to the details of this design a little bit later, but each of the junctions itself was made as a squid in this design for a particular reason, which I will explain in a little bit. So,
hey, Vijay, we do have one question already, which I wanted
sure.
to talk about very briefly, if we
Yes,
could.
go ahead.
Someone is asking, in the previous models from like IBM and Google, when we had those bus resonators and those types of couplings, what is the major source or sources of decoherence in these models?
So, well, the sources of decoherence ideally shouldn't depend on how these qubits are laid out or what are the choices of the coupler. In principle, I mean, from what we understand, one of the most limiting factors in superconducting qubits right now is basically dielectric loss, which is coming from the interface of the superconducting films to the substrate. And this was done through a series of extensive studies a few years back. And by optimizing the layout of the size of the capacitor and the gap between the capacitors and some new work with new materials, they have been able to suppress this source of decoherence. So at least to my understanding, that is the limiting factor, but it applies to almost all transmon superconducting qubits. It's not necessarily dependent on how the bus resonators are used to connect it. Ideally, it shouldn't be the case.
Cool. Great. Thanks.
Okay. All right. Anything else?
Not for right now.
Okay, great. All right. So now, if you stare at this circuit, and you might say, well, how do I actually analyze this kind of a circuit? And essentially, the way you have to think about it that, well, there are now several modes of oscillation because there are many inductors and many capacitors. So you have to really think of this as a composite circuit, which has to be analyzed for its properties. And what I will show you is that such a circuit can be represented simply as three coupled anharmonic oscillators. So it's anharmonic because of the Josephson junctions being used for the inductors, and they are always coupled in the sense that they all emerge from this circuit, and what you see is that they have a specific form of coupling. Okay, so we will see how that comes about in the next few slides. So for the people who are familiar with the Josephson parametric converter or the Josephson ring modulator, which was a very nice design of amplifiers developed sometime in the 2007, maybe I want to say 2007, 2005, maybe, where these the normal modes of a four-junction system like this was sort of identified. Okay, I was right, 2010. And it's sort of very simple to see. You can try to observe it from just the symmetry of how this device looks like. Or you can more formally actually figure out the normal modes, and you'll see that both approaches are possible. So the first mode is really just like an effective junction. You can think of this as an effective inductor with these two inductors in parallel, as in series, in parallel with these two inductors, which are also in series. So then between this terminal and this terminal, it just looks like one effective junction. So that's one mode. And it's a dipolar mode because this point oscillates with respect to this one, and in the most ideal case, these 2 points are at zero potential. I'm assuming that all four junctions are identical. Okay, we'll talk about the more general case later on. The second mode is, or before that, so we can then place this Trimon inside a 3D cavity, which has the electric field pointing in this direction as shown. And the electric field of the cavity will actually interact with the dipolar mode, which is pointed in the same direction. And that's basically what gives the qubit cavity interaction, which will be used for measurement later on. Okay? So the second mode is also exactly the same type of mode, but it is now just 90 degrees rotated. So now the plus and the minuses are like this, and now you have zero potential here. And now you can see that this mode will actually not couple to the cavity at all in the most ideal case, because it's 90 degrees. The dipole of this mode is 90 degrees to the electric field of the cavity mode. Okay. And then it also has a quadrupolar mode, which looks like this, where you can actually think of this as all the four junctions are effectively in parallel. So for example, if you connect these two plus terminals together and connect the two minus terminals together, you can basically see that all the four junctions are in parallel between these plus and minuses. But when it's spread out like this looks like a quadrupole. And that mode also will not really interact with the cavity in the general case. And basically, you can now define these mode variables. This is a standard process where you have some degrees of freedom of a circuit, which has several degrees of freedom. Then you try to find the correct normal coordinates so that the description of the system can be made in a very simple fashion, right? So here the correct choices are like this. So you define the modes A, B, and C. So the mode A is basically phi 1 minus phi 3. It's sort of obvious from this. and then mode B is phi2 minus phi4, and then the quadrupolar mode is phi1 plus phi3 minus phi2 minus phi4. Okay, and then there's a factor of 2 to sort of keep things consistent in the way we define the Hamiltonian. So once you write this down, the Hamiltonian of this ring is just the sum of the Josephson energies of these four junctions. And then you simplify it with this kind of a transformation, and you get a very nice and simple looking Hamiltonian, which is just like the product of three cosines for the three modes and the flux. So the phi is the flux in this loop. And similarly, you get sines. Now, this paper I've cited here, which is the amplifier paper where this was first done, the system actually exploited the second term, the one which is sine phi b, sine phi c. But here we always operate at zero flux, and that basically kills this term, and it's actually this term we are interested in, which now the cosine of phi is basically 1 at phi equal to integer flux quantum, and then you're left with just product of three cosines. So that's your Hamiltonian. You now add your capacitances to the system, and then you have the full Hamiltonian, right? And basically now you do the standard process of expanding this cosine terms to the first nonlinear order. And since the value of the Josephson energy and the capacitive energy is chosen in such a way that these are weakly anharmonic modes, this is a sufficiently good description of the problem, just exactly like a transmon. So these normal modes exactly behave like a transmon with a slightly different value of EJ and EC, right? So you can now have a transmon like mode A, then you have a transmon like mode B, and a transmon like mode C. That just comes from expanding. And that just gives you three qubits. The parameters are chosen in such a way that all of these three modes can have different normal mode frequencies that can be chosen by choosing the capacitors appropriately. But the interesting part comes from these other fourth order terms, which are pairwise, like phi a square, phi b square, and phi b square, phi c square, and phi c square, phi c square. And it's this term which basically tells you that in this normal mode picture, these three normal modes, which are now my transmon-like qubits, have always this kind of a coupling. Okay, and originally, we were calling it longitudinal coupling, but the word longitudinal coupling is, I think, used for many other things. So in fact, we realized we probably made a mistake by using that, even though we were sort of, there was this general notion that sigma x coupling was transverse and sigma z coupling was longitudinal. I think the phrase which has now stuck, and I think is the correct one, is the cross-Kerr coupling. And that's because the phi to the a fourth term is like a self-Kerr term, and these are cross-Kerr terms, because essentially what this tells you is that if you put an excitation in one oscillator, it actually affects the resonant frequency of the other oscillator. So that's why it's cross, and it's pairwise cross-Kerr terms here. Okay. Now, if you specialize this to the two levels and write down the Hamiltonian in terms of the sigma z two-level operator, then what you get are three sigma z operators at three different frequencies, and then you're left with this sigma z kind of coupling term. Okay, so and these terms are always on, so you really should not think of them as three different physical qubits, but more like as a composite coupled three-qubit system. Okay, that's important to keep in mind. And then, of course, the cavity comes into the picture, and we will look at that later in a little bit, which is basically how the measurement is done. So, in the transmon, you have this dispersive term which emerges from the coupling of the qubit and the cavity mode in the dispersive approximation of the Jaynes-Cumming Hamiltonian. And basically, it tells you that you have frequency of the cavity, which depends on the number state or the qubit state of the system. And then, you can basically measure these phase shifts by scattering microwaves, which is effectively probing the cavity's frequency. You get two different phase shifts, and that's how we detect the ground and the excited state for a standard single qubit. So you have something very similar here. And basically now, as I mentioned earlier, it's the dipolar mode A which couples to the qubit. So in fact, this was, we had not fully analyzed this system when we first were looking at it experimentally. We thought, oh, we will actually not see any signature of mode B and mode B that easily. But it turns out that because mode B and mode C are coupled to mode A, there is effectively a dispersive shift for all the three modes. Okay, so which means that just like in a single qubit, you have two different phase shifts for the state 0 and state 1. For the Trimon, you have 8 different phase shifts for all the 8 possible combinations of this 3-qubit system. Okay, and they typically are laid out like this, and I will comment on this. Some of them are not well separated, so how do we distinguish between them? So we will discuss that just a little bit when I come to the measurements of the device. And this basically allows you to do a joint dispersive readout, so you can measure the joint state of the 3 qubits. And the main idea here is that you can separate the 000 state from the 111 state from everything else. So typically the distribution of these states turns out like this, the phases. And this allows us to actually implement the full 3-qubit joint measurement in a sequence of measurements, not in a single shot. If all these histograms were completely well separated, we would be able to measure this in a single shot. But instead, what we have to do is we have to sort of exchange the population of one of these in the middle with the outside ones. And in a sequence of 4 measurements, we can actually recover the full 3-qubit measurement, joint measurement of the sigma z operator in this case. So this is exactly how we implement the measurement. So the way you have to now think of designing a device is that—
Hey, BJ?
Yeah.
Sorry, we have one more question, which is sort of tied to the previous
Sure.
slide. We have some people in the chat wondering what the role of those large capacitor pads are on the in the circuit diagram, and why they have to be so much bigger than the rest of the circuit.
Okay. So the role of these big capacitor pads is to provide sufficient shunting capacitances to these junctions. This is essentially how the transmon works. You want a fairly large capacitance so that the EC, which is the charging energy, which goes as the inverse of the capacitor size, is small enough, and the EJ over EC ratio is in the right transmon regime, which for transmon, it should be about somewhere in the 50 to 100 kind of range. And that is actually a property of the transmon. And that ensures that charge noise is not something we have to worry about. Otherwise, this is basically a charge qubit, and the effect of the substrate induced charge noise will give you a lot of decoherence. In fact, transmon was basically a major breakthrough in realizing that there is a combination of EJ over EC which suppresses the charge noise sufficiently, but yet it doesn't make the system so harmonic that you cannot have a nonlinear ladder and separate out the 2 states. So it's exactly the same thing going on here. There are some other features which are sort of funny in the fact that these capacitors are sort of placed in a weird fashion. They don't look very symmetric. The sizes are different, and these are actually done for a reason. The sizes of these 2 capacitor pads and these 2 are different intentionally, so that the 2 normal modes of the 2 dipolar modes have different frequencies, because now we only have the frequency to select the qubits, because this is a single circuit. Anything you apply, a field you apply, a microwave field you apply, is applied globally to all of them. So that's one reason. Then the second reason is also for this capacitor. It looks like this has fallen off from this level. This is intentional, and this is actually to introduce an asymmetry in the capacitance network as well, so that all the 4 CCs are not exactly the same. And this is done because we want to break the symmetry of this particular circuit for the reason that the cavity mode otherwise will not couple to these other 2 modes at all. Now, this is actually not for the measurement, as I explained earlier, that the measurement comes from the fact that the qubits are coupled to each other, but the fact that the microwave field is entered always via the cavity in the 3D architecture. So if these 2 modes remain completely uncoupled, there will be no way to excite them. So when we did our first experiment, we saw that we had to put a lot of power to excite the mode B and mode C. And that sometimes can affect mode A if the power is very, very large, because the mode A is strongly coupled. So even though it's off resonant, you can get stark shifts. So we had to optimize for that, and we introduced sort of a carefully control level as much as possible in fabrication to introduce the asymmetry, so that the power coupling to each of the 3 normal modes is reasonable enough to be able to work with realistic microwave powers. And in fact, this is exactly what goes on when we actually have to design the device. We first sort of numerically solve the level spacing of all the various levels which are there in the system, the frequencies, and how much coupling we will have, and then we sort of translate that design into a CAD design and simulate to see if the capacitances are coming out right what we want, and then we sort of have to iterate back and forth till we happy with the set of parameters we want. And there is some other subtleties to this which I will talk about later, and then you make the device and you get this particular device. So is there another question, Olivia?
People are sort of discussing now the difference between flux qubits and charge qubits, but I think you did touch upon that. I think you sort of answered it, so I think we're good.
Okay, yeah. So this is basically a transmon qubit, but it's 3 coupled transmons in a single circuit. Okay. All right. So then, we can go ahead and we can look at this device. So here's a result from one of the devices. You can see the normal mode frequencies are different. They are separate by about 400 megahertz here and about a gigahertz here, and that's typical with the kind of parameters we chose. And here is the anharmonicity. So this is basically the difference between the 0-1 transition and the 1-2 transition. And for those who are familiar with transmon devices, you can sort of note that this anharmonicity is a little low. It's about a factor of 2 to 2.5 lower than, maybe even a factor of 3 lower than typical transmon devices. And this comes from the fact that the junctions here for the dipolar modes are actually effectively in series. And that dilutes the nonlinearity of that effective inductor. In principle, one can design it to have larger anharmonicities, but then that will cause the frequencies to move out of the window which we are interested in. So it's not a fundamental problem, it's more a restriction of how we are doing the experiments. And you can see that the coherence times are reasonable, not as good as IBM devices, but decent for doing experiments. And I guess similar to T1s of non-IBM qubits in other parts of, in other academic labs. And this is the dephasing time. I'm quoting T5 so that these numbers look large and nice. And the most important numbers are these couplings. Now you can look at these parameters. This JAB, BC, and CA are the coefficient of the cross-Kerr terms, and they are like enormous. They are 100 megahertz. So it means that these qubits are very strongly coupled to each other. And for those of you who are familiar with NMR systems, the Hamiltonian of the system is actually very similar to NMR because they also have sigma Z kind of coupling, except that these coupling strengths are extremely tiny in relation to the Larmor frequencies. And that puts them in a very different kind of a regime of operation. But here you can actually see what this will give rise to. So you have distinct frequencies, so you can address 3 qubits, you have sufficient anharmonicity, and you have good coherence, and most importantly, you have strong coupling. So basically, you have a 3-spin system which is coupled to each other like this, very strong coupling here. Okay, so now you will sort of get a sense for what is going on now in terms of the full Hilbert space of this 3-qubit system. Okay, so there are 2 equivalent ways of thinking about it. The simpler one is to say that, okay, this is an 8-level Hilbert space corresponding to a 3-qubit system. And here's how the energy levels are spaced out. Of course, we can label each of these levels by these numbers, 0, 0, 0, or 1, 0, 0, where you can say, okay, this is the first excited state of the red qubit, if you would like. But that would be a sort of a simplistic picture. What these 2 levels correspond to is it's a transition on the first qubit. So you're putting an excitation on qubit mode A while the other 2 qubits are in 0. Okay. Similarly, if I look at this transition from 011 to 111, I have to think about this as this is a transition on, again, the qubit A. It's the first one, so it's A, B, and C, while the other 2 qubits are in the 1-1 state. Okay, and same goes for any other transition. So this one would be a transition from 0 to 1 of the second qubit or the B qubit, while the first and the third qubit, which is A and C, are in 1. So that's why these frequencies are written in that particular way. This is a transition on A qubit with the B and C in 1. Okay, So this highlights a very important aspect, that all of these transitions are actually conditional transitions. Even though this might look like a two-level system, and I would be tempted to call it a qubit, it's actually not just a qubit. It's actually a conditional rotation on qubit, a particular qubit conditioned on the state of the other qubits. Okay, so this picture then tells you that, oh, if I now do a pi pulse on this transition, then it's basically like doing a controlled NOT operation on this. And if I do any generalized rotation, it's a controlled rotation, which is controlled on the other things, right? So then you have essentially 12 different frequencies, which are labeled by these 3 colored sets of arrows. So there are 4 red arrows for 4 transitions for qubit A, and 4 green and 4 blue for the other 2 modes. And each of these transitions represents a conditional rotation. And this is where the power of this kind of system comes in, because these allow you to do a very special conditional operation in these systems. In addition, just like in a single qubit system, you can do these so-called virtual gates by just obeying the phase of your microwave drive. It's essentially equivalent to doing a Z rotation. Here, doing that for a particular transition is equivalent to doing a control theta operation. So by controlling the phases of all the transitions which link a particular level, you can actually do a control theta operation. This is essentially a virtual, what I think there was an IBM paper from some years back, which called this a virtual gate. So you have actually access to 8 virtual CC theta gates in this architecture. And these gates are very, very useful and powerful, and essentially they're free in this particular architecture. Okay, so now I've put in some typical numbers, and what you notice is that each of these frequencies of the 12 are quite distinct, which means I can address them in a frequency selective way by just sending a global field. And that's what allows you to manipulate this three qubit Hilbert space in quite a nice fashion. Okay, so now you have a pi pulse on any transition basically gives you a CCNOT gate, or this is basically a Toffoli gate. So the simplest thing you can do on this system is actually a 3-qubit Toffoli gate. The price you pay is that now lower dimensional gates become slightly more complicated. And this is because of the fact that individual qubit identity is lost in this kind of picture. So if you want to do a control NOT gate between only 2 qubits, you have to do the transitions for both of the states of the other, the third unwanted, which is not participating in this particular 2-qubit gate, and extending that to single qubit situation. You have this requirement that now I have to do 4 pulses. So I have to address 4 transitions so that all the 4 possibilities of the other 2 qubits which are not involved in the single qubit are taken care of. Okay, so a 3-qubit gate is now a single pulse, a 2-qubit gate is 2 pulses, and a single qubit gate is 4 pulses. So in some sense, the complexity has gotten reversed. Like in a conventional system, single qubit gates are the simplest, are the shortest in time, and 2-qubit gates are more complicated, and 3-qubit gates could be even more complicated. Here, you sort of have a reverse thing. But the thing to note is that these are all effectively simple Rabi rotations of a particular transition. So in principle, the fidelity of each of these single transition selective gates, as we call them, can be very high, in the high 9/9s, 3/9s or higher, depending, of course, on how you do it and the coherence times and things like that. So just concatenating them to create more complex operations is not really, that much of a drawback. At least that's not what we think. Alternatively, you can just think that, well, this Toffoli gate, the CCNOT is universal. I'm just using a whole bunch of these to control my 3-qubit Hilbert space. So you can really think about this in different ways. If you want to think in the language of single qubits, you have to say, okay, I have to apply 4 qubits. But you will see that this can also be simplified as well, and I'll comment on that towards the end.
Hey, Vijay, sorry to interrupt again, but I wanted to ask this question before we talk more about pulses. Somebody is asking if you could talk about the knobs that you have in the circuit design to tweak the pairwise J's.
Okay, so the knobs essentially we have are just the junction sizes and the capacitor sizes. So it's actually a good observation, probably, that there is not a very careful or simple way of achieving any J you like. This typical values of J's is determined by the typical values of EJ and EC, which are going to be used. So I cannot that easily make one of them very small while keeping the other ones. It is possible to some extent by introducing asymmetry. So if I make the junction sizes a little bit different, you can tune them to some extent, but it's not really like a simple knob where I have one parameter and I just turn it up and that turns this number up or this number down, and they're all interlinked with each other. But this aspect is not very important for just having a 3-qubit Hilbert space. But yes, it could be important for other kinds of experiments one might be imagining. And especially it would have been fantastic if this J was tunable in situ, and that's not really the case. At least you can tune it a little bit, but not so much that it can really be useful, say, in some kind of quantum simulation experiments.
Cool.
Okay. Was there another one?
Nope, let's keep going.
All right, okay. So now here is an example of actually measured histograms from that device. So you can see that it looks sort of like what I had shown a cartoon earlier. The 000 measurement histograms very nicely separated from 11. Of course, we've used a parametric amplifier for doing these measurements. And then all of these other things are lumped in the middle, right? I mean, just a simple comment, a quick comment here is that why are these two histograms overlapping, the blue and the red? It's because the dispersive shift exerted on the cavity by the mode 1 is almost the same as that exerted by mode 2. That's why whether it's 100 or 010, the values of the phase shift are the same, and hence the histogram positions are overlapping. This also can be tuned to some extent in the design, of course, not in situ while the experiment is happening, by playing around with the asymmetry, but not really so much. And this is something which one has to work on for the future to improve it, because ideally we would like these to be all well separated. Then in a single shot, you can get 3 bits of information. So here we have to actually do a sequence of measurements by interchanging the population of one of these with one of the outside ones, and then by doing it four times, we are able to get all the different weights of the 8 different states of the system. And then, of course, you can do standard tomography by rotating all the different qubits about X and about Y, and repeat this measurement to reconstruct the full 3-qubit Hilbert space. So that part is very standard as how you would do it for a single qubit. Okay. So we were able to do a bunch of algorithms using this, and of course, we did all the standard 3-qubit states and things like that. But these two algorithms actually sort of show off the power of this model in terms of having access to these gates. Now, this is one particular version of a QFT algorithm which uses single qubit gates, but also these conditional rotations, phase rotations, which are actually extremely simple in this particular architecture. It's just implemented in software. It's not even a real gate you apply. You just keep track of phases in your software, and that's it, by changing the phases of the pulses you're sending in after that gate has to be executed. So using this, we did a bunch of period finding experiments. We created wave functions of various periods, period 1, period 2, and so on, period 4, period 8, and then the data is the theory of what it should be like, the weights basically of all the different 8 different eigenstates of the system, and the experimental results. And it's not terribly bad. You can see good agreement between these things. And again, most of this I will comment on what are the limitations in this experiment. The one we got quite excited about was actually the Grover's algorithm. And again, as many of you know, that Grover's algorithm allows you to do this identification of the special marked element in root n steps as opposed to n by 2 steps for a classical algorithm. So here is the version of the Grover's we used. And this is a 3-qubit system, and we were able to do a 3-qubit Grover on this, which means that square root of n would have been a little more than 2 steps, but we only executed 1 step. And the reason for that is the algorithm for 2 steps was so long that decoherence essentially destroyed any advantage you could get by running the Grover step a second time. So we did what others have done in the past. We just did one step, and one step of this Grover's iteration says that you should get the correct answer with a success probability of about 78%. And these are actually the experimentally obtained success probabilities, where we chose all the different the 8 states as the marked state, one at a time. So each of these is a separate experiment. And you can see that the success probability is about 50%. It's 55 highest for the 0, 0 state, and then lowest for the 1, 1, 1 state. And that kind of makes sense because these highest states are the most unstable and most prone to decoherence. So they tend to perform worse in when used as the special state. So again, if you see here, these special the oracle step here is just these control z kind of operations, control theta, which are again free. The price we pay actually is in these single qubit rotations, which are needed several times in the Grover's algorithm. And in the beginning, it is to create the equal superposition state, and that's actually the most complicated for us. You need to apply all the 12 pulses to be able to create that, and that increases the number of steps you have to do. But despite that, what we found was that at least at that time, even though the paper got published only very recently, this result is now almost 2 years old. We actually saw that we did better than the best known result for a 3-qubit Grover at that time. And this was actually on that 5-qubit trapped ion system I had talked about earlier. That was 11-qubit system, but they had done some experiments on the 5 qubits. And this system also has the ability that it is all-to-all coupled. But the native gate in this ion trap system was a 2-qubit gate, whereas the elementary operations in a Grover's algorithm for a 3-qubit Grover's algorithm are actually 3-qubit gates, and that means they had overhead on that front. And we actually were able to do better in terms of the average success probability for a single step of the Grover's algorithm. And then more recently, we actually ran this on one of IBM's 5-qubit system, which again, the connectivity is, because it's only 3 qubits, we could choose 3 qubits which were all-to-all connected. But the native gates were again 2-qubit gates. And in order to implement the form of Grover's algorithm we did, there was a little bit extra steps they had to do. Of course, the single qubit gates were a lot easier, and we saw that it was sort of similar performance. Of course, this number varies depending on when we do it, on which pair of qubits we choose, but this is sort of typically what we got. So this sort of told us that, well, there is really something interesting here, that by reimagining how the qubits are designed, one might be able to get some advantages. So there are a whole bunch of course, issues to be solved. And this basically has got to do with the level structure. Now note that I've only shown the 0 and 1 excitation of each of the modes, but this is an anharmonic ladder. There are the second excited states of each of those. And it's not so impossible to imagine that the 2 excitations, one each in qubit mode B and C, might have an energy very close to the state 200, which will be close to this. And then if it comes very close, then isolating that in frequency space can potentially become a problem. So the optimization I talked about during the fabrication step, we have to sort of do this numerically and try to find the correct parameters so that all these unwanted states are far enough. And we had a situation in this experiment where the nearest sort of bad level was only about 19 megahertz away, and the next nearest bad level was about 30 megahertz away. Now, this is, of course, much smaller than the anharmonicity, and then that means that you have to do your gates a little bit slower. All of these pulses have to be slower. So we were typically using Rabi rates, which were much less than 3 megahertz, so quite slow compared to typical transmon experiments. The other thing was that, remember, I told you you need 4 pulses, each of these red transitions to do a single qubit, an effective single qubit gate on the first qubit. Now, because these are distinct frequencies, in principle, they can all be applied at the same time. I just have to make a composite pulse with 4 different frequency terms and then send them together, as opposed to doing it sequentially, which is how we did it in the first experiment. And that was just because of technical reasons. And one needs to also play around with the power that is available on your AWG if you want to be able to do this properly. And so this will actually then make this notion that it's 4 pulses really spaced time versus one multi-frequency component pulse. So that will help a lot in terms of reducing the time of execution, especially for algorithms which have lots of single qubit gates. So this is something we are working on for the future. And of course, we should ideally like to tune the dispersive shifts and see if it is possible to reduce the number of steps it takes to do the measurement. And that will also be important. Okay, so Olivia, I have another 10 minutes.
Yep, go ahead.
Okay, great. So I will tell you a few other experiments which we have been doing and trying to sort of extend this idea. One obvious question was, of course, well, what if I put more junctions in the loop? And turns out that the idea, at least at that level, works fantastically well. So here we actually made a device. This one we called a pentamon. It has 6 junctions in a loop and hence 5 normal modes. Again, now the normal modes are no longer easy to visualize, but you can really think of this as a problem of 6 mass spring systems sort of connected with the periodic boundary conditions. And basically, those are the normal modes you get for this kind of a system. So we were able to make this device. We were able to identify the 5 different modes, measure the anharmonicity, and now you see that the anharmonicity is even weaker because now there are, in some sense, there are 3 junctions in series as opposed to 2 junctions in series. And this was, the only first device we made. The T1s were not as impressive as the previous ones. But we are also able to check that indeed every junction or every effective mode is coupled to every other mode. And these are all the extracted values of the coupling parameter J, which is the coefficient of the sigma z term. And you can see there's a fairly large variation. And this again depends on the details of the devices, but this would be the typical range. But then we did not pursue this device further because we realized that now I have to optimize a 32-level Hilbert space. So this clearly is not the way to go for just building a universal quantum processor, because essentially all the advantage you get by going to large number of qubits is completely defeated here, because you now are actually working with a 2 to the n level Hilbert space with 2 to the n things to control, and that's just not going to work. But we have some other ideas for what one could do with these kind of systems which have more number of qubits in the junctions. Okay. So instead, we said, well, what if this 3-qubit building block, it's interesting because now we can do a native 3-qubit gate. It seems to have good coherence properties. It's nicely coupled. What if this is used as a building block to make a larger processor? So first we thought about, okay, can we make 2 of these interact with each other with some coupling element? And then after some back and forth, we realized that this might, again, lead to too many levels to be playing around with. So we came with a slightly different idea where we're going to mediate the interaction between 2 trimons with the help of a single transmon. Okay, so we in this direction, and we wanted to also use the cross resonance gate because these are fixed frequency qubits, and that's the most natural way of doing gates in this kind of architecture. So as a first step towards this idea, we did an even simpler experiment. We built a multimodal qubit, which we now call daimon. Okay, this is basically the 2-qubit version of the trimon. And you can think of that as just by shorting these 2 terminals together. So it kills one of the dipolar modes, and then you're left with just one dipolar mode and one quadrupolar mode. So it has 2 modes, but it's still exactly the same type of device. It has sigma z coupling. This kind of a device has been used extensively for other, and they also have other names. It's also was called the 3-island transmon some years back. And then more recently, in fact, Zlatko had done this fantastic experiment for his Ph.D. Using a device which has sort of a similar structure for catching this quantum jump. So we took this 2-mode device and coupled it to a transmon. And now this is how the Hamiltonian looks like. So this first part is your multimodal qubit Hamiltonian, 2 qubits coupled by a sigma z. And then the third mode, which is the transmon, is now coupled transversely, but only to the one of the modes of this qubit. Okay, so I think there's a little typo here. It should be coupled to the mode A, which is the dipolar mode, and not the quadrupolar mode, which doesn't couple to this particular qubit. And now these 2 qubits can be just treated as 2 different 2-level systems with some detuning, and we can use the cross resonance architecture basically to drive a cross-resonant interaction between the transmon and this conditional transition of the diamond, because effectively this is the two-level system with respect to which we are doing the cross-resonance architecture. Now, since we were doing this for the first time, both the cross-resonance and also we were not sure how the multimodal system will behave, we actually did a sort of an intermediary experiment where we studied the dependence of the cross-resonance gate as a function of detuning. So for that, we did a 3D cavity experiment with this 3-cavity system, but in a copper cavity, so that we could apply a magnetic field from outside to tune the transmon. So the transmon here was tunable, so that we could now study how the cross-resonance works as a function of the detuning. And then we were able to adapt a theory which was developed by some of the IBM scientists for the cross-resonance. We saw very good agreement, and then we identified these good, so these blue and sort of orangish bands are the correct range of detunings you would like to do the best possible cross-resonance gate. So we used this to identify the parameter space, and then we made devices now with a fixed frequency transmon chosen to have the right detuning, and now in a regular aluminum cavity to do the experiment. The copper cavity causes other problems in terms of decoherences, because these are bridge qubits. When the metal comes very close to copper, you get strong dissipation. So here we are not worried about the coherence more, but more about the 2-qubit interaction, whereas here we wanted to get the coherence reasonably good to be able to do a good 2-qubit gate. So here are the ZX term which you get in a cross-resonance architecture as a function of drive strength, and then this is sort of the operating point we chose to operate our gate, and all of this agrees with the very nice theory quite well. And we did basically the ZX by 2 as our elementary gate, and did a standard and interleaved 2-qubit RB, and extracted a randomized benchmarking fidelity of 93.4% for the standard, and for the interleaved about 97%. The coherence limit we calculated from simulations was just a little bit over that. So given all the coherence times, which were again sort of in the tens of microseconds, this is anyway the best we could do. So this sort of convinced us that this idea in principle works. You can do a cross-resonance gate between a transmon and a conditional transition of the diamond. So now we just have to extend this. So this is now stuff for the future. So far what we had done is that we had done this 4-level system, which was the diamond and the transmon. We just have to extend it to now a full trimon. The experiment actually remains the same, it's just the device is different. We're still doing a conditional transition, choosing a conditional transition of the trimon and doing a gate with that. And this actually would give you a control kind of operation. So it's a CCC rotation or not, whatever you would like. And then the idea is that, well, how do we make this qubit interact with other qubits or other modes of the system? Now, one could do a conditional operation with a different mode, but the couplings might not be the same, because remember that only the dipolar mode would couple strongly to this device. But because the interqubit operations of the trimon can be done with fairly high fidelity, one of the real advantages here is that you can swap the populations very easily between different qubit modes. So that way you can do the interaction always with this level, and then just bring the qubit into this mode, whichever one you like. And in fact, one of our first experiments, we had shown that you can do these sort of qubit swaps very easily, and can be done with quite high fidelity. So even though it adds a little bit more steps, overall, the advantages should be retained quite nicely. So in the end, what you would have is that you have all the 3 modes of the trimon coupled to each other, and coupled to the common transmon sort of via this interaction. So then this can be used as a way to add more blocks in the system and create a larger experiment. So one experiment which is sort of planned for the future is to have 2 trimons mediated by 1 transmon. So that would effectively be a 7-qubit system or a 6-qubit system, depending on whether you want to count the transmon also as a actual qubit, or it's just an intermediary doing the experiment. So this is something which is there for the future. And more recently, we actually got excited by these new results from the Waldorf group, where they introduced another all microwave controlled phase gate for fixed frequency far detuned qubits. And we did some preliminary experiments, and it seems like quite a robust idea, and that can also be used. And the advantages here as compared to, or the differences as compared to cross resonance, are the requirement for anharmonicity and other things are a little bit different. So maybe it can be used for certain combination of frequencies, whereas the cross resonance could be used for a different combination of frequencies. So we've been looking into that as well. So that's basically the story I wanted to say. I hope I have shown that the Trimon is a strongly coupled 3-qubit system with always-on cross-Kerr coupling. It's good single and multi-qubit control, with which you can do very high fidelity CCNOT and Toffoli gates, which are native to this architecture, and that leads to efficient implementation of algorithms where such gates are important. And as a first step towards scaling this up to larger number of a larger processor with the multimodal units as the building block, we did some cross resonance operations between a transmon and a diamond. And that's it. So that's a group picture from last summer. And these are sort of the general ideas we are working on, looking at new out-of-the-box ideas for what qubits are. There's a big focus on developing low noise amplifiers. And again, we had done some work which used a multimodal nature to enhance the bandwidth of such amplifiers. More recently, we've started putting together teams and resources for building small-scale quantum processors, and again, something which could potentially be accessed through the cloud, and sort of working towards one of, an area where I would like to contribute quantum error correction, but we are still putting together. And the ideas of high connectivity, and there are actually other new projects where we are again trying to build more connected superconducting qubit networks with error correction in mind. Because I feel that if we can make a block of a small number of qubits, which are a lot more strongly networked, maybe we can create an effective logical qubit out of that in a lot more efficient way than that is currently possible. Okay, so I will end there, and thank you for your attention, and I'll take any more questions there.
Thanks, Vijay. This was really great. I really like, anytime I get to talk about this. Thanks, Vijay. This was really great. I really like, anytime I get to talk about things that are related to the amplifiers, because that was what I did, obviously, and I don't get to talk about that so much. So we do have a few more questions. Let me just go back. Some people I know were asking about the coupling, that lime green line you had in a previous slide between the Trimon and I think the diamond. And people were sort of asking how you're actually going about creating that coupling.
You mean this stuff?
Yeah, people were asking about this slide, I believe.
So the coupling is done just like how you would do for any two transmons. So if you look at this this device, so in fact, let me see if I can zoom this here. It's basically the two things are kept next to each other, and the extreme cavities are the readout cavities. So this qubit, the transmon, is coupled to both the readout cavity and the central cavity, which is the intermediate cavity. Right? And similarly for the diamond here. So because these are aligned with the dipolar modes of the cavity fields, you get a coupling between the diamond and the transmon mediated via the cavity. This is exactly how you mediate interaction between two transmons which are coupled by a bus resonator. The difference is that this diamond is a slightly more complicated circuit where it has both a dipolar mode and a quadrupolar mode. So of course, the dipolar mode of the transmon will not interact strongly with the quadrupolar mode of the diamond, but it will only interact with the dipolar mode. So that's it. It's just by putting them basically coupled to a bus cavity. If you had to do this without a bus cavity, you would really just make a single chip and make the transmon right next to it. So it's just the fact that these two are right next to each other, you'll get capacitive coupling between the two. Okay, so I hope that answers the question.
Makes sense to me. I have another question here.
This is just a cartoon representation of what's going on. Yeah. Yes, go ahead, please.
Sure. I have another question here. Can you comment on the Trimon diamond modes that you use for the cross resonance operation with the coupled transmon?
Right. So we have so far not done any experiments with the trimon coupled to a transmon. That's the next step. And this was just purely, I mean, after having done this experiment, we felt that, okay, maybe we should have done it with the trimon itself. It was just to keep things simple and have to worry about less things. And because the physics is basically the same, that's why we chose this. So what's really going on, right? So let's first just consider the diamond. The diamond is just a 4-level system, which is described by this Hamiltonian here. So it's 2 qubits with the sigma z coupling, the cross-Kerr coupling, which means all of these 4 transitions are distinct, just like all the 12 transitions in the trimon were distinct, which means I can control this Hilbert space completely without any problem. Now, in order to create an interaction between the diamond and the transmon, we now have to look at this 2 as the effective 2-level system of the diamond which we are choosing. Now we know from our analysis that this is not one of the qubits of the diamond, but it's a conditional sort of transition, right? This is the transition on the first qubit when the second qubit is in 0. Similarly, this transition here would be the transition of the first qubit when the second qubit is in 1. That's the way we interpret these transitions and levels. So if you now forget, these, if you sort of forget these 2 levels, then you just have 2 2-level systems to worry about, and that's your 2 qubits between which you are doing a cross-resonance gate. So all the same things apply. So we use the transmon at a higher frequency than the diamond, so that we can choose the control and the target appropriately. And then, so we basically drove the transmon at the diamond's frequency. So this is the control and that's the target. And then everything else just like how it would work in cross resonance. This, the same arguments for anharmonicity plays a role. The only difference is that the interpretation of this operation. So if I actually do a control NOT operation between these 2 qubits, it's actually a controlled NOT, because the third qubit has to be, which is this green qubit, has to be in state 0. So it automatically again implements a CCNOT operation because of the conditional nature of the diamond transition. Okay, so I hope that's clear.
All right, I got maybe one more question for you. And I think this is sort of a future question. Have you guys thought at all about doing any type of error correction with these new systems?
That's a great question. In fact, when we first did the Trimon experiments, we thought, hey, here is a well-controlled 3-qubit system, and one of the simplest 3-qubit error correction we know is the bit flip error correction. And in fact, that was, as I said, the motivation, one of the angles from which we were trying to work towards these highly connected systems. But then we realized that the standard interpretation or the requirements of a 3-qubit error correction is not really satisfied by this model. This is not, we haven't sort of fully abandoned it. There might be a different encoding which might work. And the reason is very simple. When we talk about error correction, and let's say we take the example of the Shor's bit flip code, but of course all error correction works on this essential idea. It's that once you have done the interaction and create an entangled state, the qubits are no longer interacting with each other. And it's essentially this aspect, coupled with the fact that environment can only do local operations, gives you the protection against errors which are happening at the level of a single qubit. Simply speaking, you basically say that the environment doesn't know how to do 2-qubit gates or 3-qubit gates. It can only do 1-qubit gate, if you want to think in that terms. However, the most natural operation here, because these transitions here are conditional by design. So if you think about a bit flip error between one of these transitions, which let's say would happen, that actually is the worst kind of error you can have, because the Shor's code is not going to protect you, because it's actually a coupled, it's a 3-qubit gate. So in this architecture, the environment, the way we have chosen our qubits, the environment is able to do a 3-qubit gate. So the protection against the fact that the qubits are entangled and hence any local operation cannot change the entanglement doesn't work anymore. In fact, it took us, when we were thinking about this, like, oh, this is completely different. But we are talking to some theorists that maybe a different choice of encoding might allow you to recover the same effective properties. But that's something we are sort of, it's on the back burner. We haven't had much time to think about it. But that's really where we would like to go, is that, one standard approach people are following, of course, is to do the surface core, where you have sort of a fabric of qubits. We are saying, well, is it possible to create a small cluster of qubits into a effective logical qubit? But we don't have any firm ideas on how to do that yet. But yes, this would be very, very interesting, and that's sort of the ultimate goal where all of this is ultimately heading. So hopefully soon.
Yeah, that seems to be a big challenge. All right, I actually lied. We have one more question, which people really want to answer. So people are asking what you do essentially when you have two states that are too close together, whatever that threshold limit is. I think people are specifically asking about the 001 and the 010 state. I think the question is, why are they so close together?
Right. So see, none of these levels are close to each other the way what has been shown here. But the things we worry about are states like 2, 0, 0. Now remember that all the 3 qubits have similar frequencies, which means that excitation energies are of the same order. So here in this state, there are 2 total excitations, and here also there are 2 total excitations. So which means this state 200 could be hovering very close to 011. Similarly for all the other possibilities. And it's the same argument you apply for just a single transmon. You have your 0, you have your 1, and you have your 2 levels. If this transition and this transition was too close, which would translate to the qubit not being sufficiently anharmonic, then when you try to do any control of these 2 levels, you're going to leak your population into this, right? And this is well-known leakage errors. So what does it constrain? It constrains the fastest gate you can do on these 2 transitions. With the help of some pulse shaping and using things like drag, you can minimize these effects. And same thing goes here. So of course, if we make a device and we find that one level has ended up too close, then that device won't be very useful. So in the experiment we did, it was sufficiently far away that we were still able to use it. But we did not do, in fact, in that first round of experiments, we didn't do any of the standard techniques for making your pulse shapes more efficient. Doing that was an optimization we had not gotten into at that stage. So of course you can do that, but if a particular device is, you try to make a device with certain properties, but we all know that fabrication uncertainties are always there. And if that results in a particular transition ending up too close, then we just have to discard that device and make a new one. So there is no in situ way of doing this. Now, having said that, it was partially the reason why we did this. Okay. Now, just to, if you sort of wait a second. How do I this? If you look at this carefully, these junctions are actually broken here. So 2 of the junctions are actually single junctions, and 2 of them are squids. And the reason we did this is that, remember that we want 0 flux in this big loop, that is the Trimon loop. But by going to successive integer flux quanta, you can change the EJ of these 2 squids. And that then allows you some amount of in situ tunability of the level structure. So we had kept this for our experiment, but it turned out that the best operating point was actually at 0 flux at these 2 loops as well. Just a side note, the reason the device was made like this, where the single junctions also look like squid, was for fabrication reasons. It was causing some stress problems, which was resulting in the junctions to break. So we actually made it as 4 identical squids with just a small break to make it effectively a single junction. So that's all you can do. So you can have some in situ tunability. Now, of course, part of the constraints here are related to the choice of the 3D architecture, where doing an in situ or a fast flux control, which can locally, say, control the EJs of all the 4 junctions. In principle, it's possible. That's not so straightforward to do in 3D. And for whatever reasons, I'm a big fan of the 3D architecture for its modularity and reproducibility. We are sort of stuck with this. We are now starting to make devices more in the conventional 2D architecture. Then, of course, it's possible to now have 4 flux lines which come very close to 4 squids, and then I can tune my EJs in situ to whatever value I want, and then tune the control. But in some, it's nice for an experiment. It's not really a very scalable way. You now need many, many lines per qubit, but not so much. It's 4 lines for 3 qubits as opposed to, say, 3 lines for 3 qubits. So really depends on what you're doing. Okay.
All right, thanks again, Vijay. So I think we got to most of the questions. So at this point, I just want to thank you again for taking the time to be here with us today. I thought that was a really, really clear and good talk. So thank you very much.
Thank you.
And we'll see everyone next week at the same time.
Right. Thank you. Thank you, everybody. Bye-bye.